There we go. Second to last section. It's already been declared. We're doing 2 sections today, I guess. Wow, that's so ambitious of me. We do that often. Yeah. Power up, power through. What's really nice is we've already done conditional probability without calling it that. And so now we're just going to assign a little formula to it, nothing crazy. But first, if you are playing cards, for example, right, and there's cards out on the table, you can see which cards out of a deck have already been dealt and played potentially, right? And depending on your memory, you can remember which ones have been played, right? And so then, depending on your memory, you might be able to remember which cards have already been played. Now, why would that be beneficial? Because the probability of new cards is dependent or conditional on the cards that have already been played, right? So knowing that, for example, 3 kings have already been played, right? If you start with a full deck, you know that there's 4 kings in a deck of 52. And so then if you know that 3 of those kings have already been played, now you have, well, 3 less cards, so 49 cards, but you only have 1 king, right? And so now that probability is affected by what's already happened. And so that's what we call conditional probability, right? The probability changes depending on or conditional on other events. So maybe let's write that down. The probability of an event depends on / is conditional on, just to use the same terminology, although we're going to use the dependent, independent in the next section, and so kind of worth noting. I'll clean this up. We're conditional on a previous event. Another example is if I ask you, hey, what's the probability that it snows tomorrow? Right, you have some idea of, okay, judging by today, kind of unlikely, still possible, sadly, but right, let's say 20%, lower, 10% chance, 0.1. And then we backpedal it to 3 months ago, then the probability of it snowing is a lot higher, right? Because we know, okay, we're in that season of snow and it just makes more sense. And so knowing what day it is or what season we're in, right, is going to impact the probability of it snowing, for example, or sunny or whatever you want to talk about, right? And so that's the idea behind conditional probabilities. So before we introduce any formulas, a conditional probability might look something like this. So a family has 3 children. Find the conditional probability of having 2 boys and a girl, given that the firstborn is a boy. So now you know that the firstborn child has to be a boy. Okay? And so I think the easiest way to solve these is by drawing our tree of all the possible outcomes, right? Drawing our sample space essentially. And we get, so we've got 3 kids. And we're just going to assume boy, girl. So child number 1. Child number 2. Can be either boy, girl, boy, girl, boy, girl. Or child number 3. This is probably as complicated of a sample space that I would expect you to do on the final exam, right? On some of those assignment questions, you're rolling 2 dice and you're drawing out your sample space, but it's a 6x6 matrix, and yikes. So that's annoying, right? And so I'm not going to make you do that. I think this is the biggest sample space that we could have. So what is our sample space? Well, it's the combination of outcomes in this case at the end. Boy, 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 girl. Oh, boy. Boy, girl, boy. Oops. Boy, girl, girl. Girl, boy, boy. Girl, boy, girl. Girl, girl, boy, girl, 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 good girl. That's our sample space. Okay. Now, we're given that the firstborn has to be a boy, right? There's only a subset of our sample space that satisfies that, right? And so the firstborn has to be a boy. Okay? And then we want to know some probability out of this smaller subset, right? And so what we're interested in are all these possible outcomes, right? So now this is out of our possible 4. Yeah? And so given the first child is a boy, we want to know the probability of having 2 boys and a girl, but also knowing that the firstborn is a boy. Yeah. Now, we want to have 2 boys and a girl. This does not satisfy it because it's 3 boys. This one works, right? Boy, boy, girl, that's one of the options. Boy, girl, boy, that's another option, right? And then boy, girl, girl doesn't work because that's 2 girls and 1 boy, right? And so here, this one works and this one works. So we have 2 out of those 4 options that work. So we can say the probability of 2 boys and 1 girl given first is a boy is 2 out of 4. There's a little bit of notation that we're going to see eventually, so why not bring it up here? But given is usually denoted by kind of a tall-ish vertical bar. And so, for example, we can write the probability of A given B. You're going to read this as the probability of A given B. Oops. So we use that shorthand of the vertical bar to denote a conditional probability, right? Knowing that B happened, that's going to affect the probability of A, potentially. Okay. Nice. So you can solve these problems without any formulas or anything like that, but we will introduce a formula that I think makes it a little bit easier. Okay? And so what did we do here? We found the number of outcomes where the first child was a boy, right? The number of outcomes satisfying this given criteria. And then we found the number of outcomes out of those that satisfy the initial criteria, or A, if we want to be generic about it. Let's do another one. And like I said, you have the tools to solve these already without any formulas. So that's nice. One six-sided die is rolled once. Find the probability that the result is even. Well, what's the sample space? If it's even, it can be 2, 4, or 6, which is 3 out of the 6 outcomes. So for A, the probability of an even roll is 3 out of the 6 possible outcomes. Right? Because S, our sample space, can be 1, 2, 3, 4, 5, 6. Find the probability that the result is even, given that the result is greater than 3. So now the result has to be greater than 3. So we know that it's 4, 5, or 6. And so here the result is greater than 3. So I've got 4, 5, or 6. And now I have 2 of those that are even. So for B, the probability of even, given that it's greater than 3, is going to be 2 out of 3. Which is different. Same thing. Toss a coin. A fair coin is tossed twice. Find the probability that the result is 2 heads, right? And so you can make a tree, right? Heads or tails, heads or tails. You're only tossing it twice, so it's kind of a simple tree. I'll just do a mini version here. Heads, tails, heads, tails, heads, tails, right? That's 2 tosses. So from here, my sample space is going to be heads, 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 tails, tails, heads, tail, tail. Right, 4 possible outcomes. If I want the probability of 2 heads, that's head, head. That's only 1 of those 4 possible outcomes. So I have 1 and 4. Find the probability that the result is 2 heads. So same thing, but given that at least 1 head is obtained. Right? So now you know something about what happened, right? It can be this one, right? That's 2 heads. Here's 1 head. Here's 1 head. So the only one that's excluded is when it's both tails, right? But now we know that one of those 3 had to happen, right? And heads, heads is 1 of those 3. So what we can write is we can write the probability of heads, heads, given at least 1 H is 1 in 3. And at this point, I think you're thinking, oh boy, wouldn't it be so nice if we could just have a formula to use instead? I know that's what you're thinking. Let's see here. I need more space. Bless you. Can I move this up? Nice. Well, here's your formula. Oh, it's kind of, it went weird, but that's okay. For two events, E and F, just generically, I usually use A and B, but she likes to use E and F for some reason. The probability of E given F is given by this formula. So you have the probability of E given F is the probability of E and F. Okay? And so what we did was we had to find all the outcomes in that smaller subspace that satisfied the criteria, right? And that's the probability of E and F divided by the probability of F, which is that overall, that bigger sample space, or the bigger subset of the sample space. So the trick is going to be reading the question and figuring out, okay, well, how can I translate some of the information that I've been given into probably 2 out of 3 of these equations, right? The probability of E given F is usually what we want to solve for, but we could use the probability of E and F and the probability of F to do that. Or, right, if I give you the probability of E given F, then you can solve for one of the other 2. So a single die is rolled. Use the above formula to find the conditional probability of obtaining an even number, given that a number greater than 3 has shown. We already know the answer, right? Because we already did it. We already know how to do this, okay? Or at least we know the answer, right? The probability that the result is even, given that the result is greater than 3. 2 out of 3. But why? Why? So we want to find, let's see here. Well, first we need to translate the question into a formula that we can solve for. And so we want to find the conditional probability of obtaining an even number given that a number greater than 3 has shown. So the probability, let's translate these or do some shorthand here. E can be an even number. Oops. And to match her formula, she uses F. Yeah. And so let's just, let's use F. Oops. F can be a number greater than 3. We already said that the probability of E, we know the probability of E, an even number out of 6, 2, 4, 6, that's 3 out of 6. And the probability of F, a number greater than 3, and I'm going to clarify not including 3. Because that can be confusing. That's 4, 5, or 6 out of the 6 possible options. So that's 3 over 6. So now we have those pieces, but we want the probability of an even number given that, given F, where it's a number greater than 3. So if we translate this into this equation here, probability of E given F, luckily they match up. is the probability of E and F over the probability of F. So we have the probability of E and F divided by the probability of F. Oops. We know the probability of F, and we also know the probability of E and F, right, is the even numbers out of the numbers greater than 3, bless you. So the probability of E and F, right, has to be even and it has to be greater than 3. So 4 or 6, right? But that's out of the 6. And so here, this is going to be either 4 or 6. So the probability of E and F is 2 out of the 6 options. Now you can use your calculator, right? 2 over 6 is 1 over 3.333333, right? You don't need to use the fractions, but I'm going to use the fractions just to show you that they'll cancel. Okay. And that's always going to be the case because they have the same denominator. So we have 2 over 6 divided by the probability of F was 3 over 6. When you have a fraction over a fraction, you're going to flip the denominator and multiply them, right? And so what you get is 2 over 6 times 6 over 3, but 6 over 6 is going to cancel to 1, and you're left with, ta-da, 2 over 3, which is what we found. So that's what I mean. You can already do these questions without the formula, but eventually it's going to be easier with the formula than without. All right, let's confirm. That is what we found, 2 over 3. So you already know how to do it. So there, we're done for today, I guess. No. Any questions about that, though? So sometimes it depends on the information that you've been given. And sometimes I'll give you a table of information like this. This is called a contingency table. And that doesn't matter. It's just a table of counts. Okay. And so the following table shows the distribution by gender of students at a community college who take public transport and the ones who drive to school. And so they declare that the events M, male, F, female, T, public transportation, and D for drive are self-explanatory, mostly because they assign them in the headers. So that helps. And we're going to find some probabilities. Now, if you have a table like this, I think the easiest way to find probabilities is just use the table and just read the table, right? And I wouldn't recommend using the formula for these. If you want to find the probability that someone drives to school, given that they're male, right? So now, if you were to read the table, right, we're told that this person that we're talking about has to be male, right? Which restricts us to this column, right? And so now our total is out of 47, right? And so now the probability that someone drives out of 47 is 39 out of 47, right? Just by looking at the table. Let's see here. 39 out of 47. Or if you prefer, you could use the probability of E given F is, now the breakdown of the formula, I'll give it to you, of course, but it's the first one and the second one divided by the probability of the second one. Right? And so it's going to be the probability of E and F divided by the probability of F. In this case, for A, if we have the probability of D given M, same scenario, right? Just map wherever you see an E, you can write a D, and wherever you see an F, you can write an M, or that's why it helps to just kind of remember how the formula plays out, D and M divided by the probability of M. Probability of D and M, let's erase this all. Oops. They have to drive and be male. That's 39 out of 100, right? And so the probability of driving and being male is 39 out of 100. I'll do it down across, I guess. Divided by the probability of being male. Now the probability of being male is 47 out of 100. So 47 out of 100. But once you flip and multiply, those hundreds are going to cancel out, and you're just left with 39 out of 47. In this case, I find that just looking at the table and kind of letting the table guide you and restricting the total from the table is a lot easier, right? And so this is from reading the table. Whichever way you want to do it, fine by me. I don't have a preference. I'll show you both so you can decide. But if you have a table, I think it's easier to just read the table. Sometimes I'm mean and I don't give you a table though. Probability that they are female given that they drive. So now we know that, well, we know this about them. They drive. So now our total is 79. Now we want to know, okay, well, what's the probability that they're female knowing that they drive? Well, that's going to be this 40 out of 79. Okay. Or we can use the formula. Okay. The probability that they're female given that they drive is the probability of female and drive divided by the probability of driving. Now the probability that they're female and they drive is 40 out of 100, right? And so those totals are always out of the overall total. And so it's 40 out of 100 over the probability that they drive, which is 79 out of 100. Which 40 over 100 times 100 over 79. 100 times 100, or 100 divided by 100 is 1, and you get 40 divided by 79. I guess I'll so we've got one more. The probability that they're male knowing or given that they take public transportation. Now, we know that they take public transportation, right? 21 of the 100. then the probability that they're male is 8 out of those 21. Or, if you prefer, probability of male given T is the probability of male and T divided by the probability of T. I got sloppy. I stopped using the intersection, started writing and. That's okay. As long as you are okay with reading both. Right? This should look like this. And T. The probability of male and public transportation is the intersection here at 8, but it's divided by 100. Technically, oops, over the public transportation, which is 21 out of 100. Which is 8 over 100 times 100 over 21. Cancel, cancel. 8 over 21. So long. But it'll always work. But so will reading the table if you read it carefully. That's the glitch, usually, if you don't read the table carefully enough. I'll make this bigger. Dink. So in this case, we are given some probabilities. We're given that the probability of E is 0.5 and the probability of F is 0.7 and the probability of E and F is 0.3. And we have to find the probability of E given F, but also the probability of F given E, which will likely be different. So here we go. In this case, I don't really see a way out of using the formula. Because I have all these probabilities, and so I may as well use them. So I want to find the probability of E given F, which is E and F. So the probability of E and F divided by the probability of F. Which I have. We're told that the probability of E and F is 0.3. And the probability of F is 0.7. Probably not that great. Ugh. I'm okay if you leave it like that, or if you give me a decimal answer, that's fine too. 0.428571426. Probably keeps going, but whatever. What's a rule about probabilities that we need to keep in mind? Probabilities have to be between 0 and 1. Right? So if you get something that's bigger than 1, something went wrong. Probability of F given E, why do I say it should be different? The probability of E and F is the same as the probability of F and E. It doesn't matter, right? A and B, B and A, right? But I'm dividing by a different number, right? Depending on the information that I've been given. So here, therefore, the probability of F and E, we use those interchangeably, is also 0.3. So then I can use the equation for part B. The probability of F given E is the probability of F and E over the probability of E this time. Probability of them happening together is still 0.3, but the probability of E is 0.5. 0.3 divided by 0.5, I get a beautiful 0.6. If E and F are mutually exclusive events, of drawing on not even last day, but last potentially 2 weeks ago. Yikes. What does it mean to be mutually exclusive? It can never happen at the same time. It echoes in here. Which means, in terms of probabilities, right, the probability of E and F has to be 0. Right? There's no outcomes in common. They can never happen at the same time. So the probability of E and F must be 0. So if we want to find the probability of E given F, I sense a 0 coming on. Probability of E given F, but we'll work through it, is the probability of the first and the second divided by the probability of the second. So knowing that they're mutually exclusive, I get 0 divided by 0.9. 0 divided by 0.9 is still 0. You want to make sure that you never divide by 0, right? That's illegal math. Illegal math. Ugh. I need more space than that. Did I skip something? No. I'm just that speedy, I guess. Or maybe not. Oh, maybe not. Time flies when you're up here. If I give you that the probability of F given E is 0.5, and the probability of E and F is 0.3, then you can find one of those 3 components, right? I can give you 2 and you can solve for the third. And so we know that the probability of F given E is the probability of F and E divided by the probability of E. We're given the probability of E and F, but that's the same as F and E. And we're also told that the probability of F given E is 0.5. So 0.5 is 0.3 divided by the probability of E, which is what I want to solve for. How can I do it? I would multiply this probability of E over here. Now, this is just a placeholder for a number, right? This probability of E, and so you treat it as one thing. You're going to multiply it over by the 0.5, right? And then divide the 0.5 over. And so it's going to look like this. A little something like this. Oh. .3 divided by 0.5. Which we just did is 0.6. It's a family of 3 children again, so I'm gonna steal that tree that we made. Should have made it more beautiful. Hey, that's actually pretty nice. We're probably interested in something different, but nice place to start. We want to find the probability of having 2 boys and a girl, given that the family has at least 2 boys. And so, to translate what we want into an equation, and maybe I'll do it down here, the probability of 2b and 1g, given that the family has at least 2 boys. Let's translate that into the probabilities, right? Instead of using the tree to solve this, right? Let's find the probabilities. This is your E given your F, right? Which means you want the probability of 2 boys and a girl and at least 2 boys in your numerator. Probability of 2 boys, 1 girl, and at least 2 boys divided by, right? This is an and here, divided by the, oops, I need a pencil. The probability of at least 2 boys. These probabilities are out of the total sample space of 8. Right? Each of these probabilities. Yeah. So 2 boys, 1 girl, and at least 2 boys. And so we have 2 boys and a girl, 2 boys and a girl, and a girl and 2 boys. Because it has to be the overlap of at least 2 boys. So I'm seeing 3 out of 8 that are satisfying this criteria. So I get 3 out of 8. I'll highlight that and I'll use a different color. The probability of at least 2 boys, right? At least 2 boys happens here, it happens here, it happens here, happens here. So I get 4 out of 8 that are at least 2 boys. And then once I have 3 over 8 multiplied by 8 over 4, I get 3 over 4. Which, if we look at our highlights versus our pink check marks, I know, no rhyme or reason here, but I have 3 out of the 4 that satisfy that criteria. So you could have found it with just the tree if you want it. Nice. Any questions about that one? That one's kind of big. At a community college, 65% of the students subscribe to Amazon Prime, 50% subscribe to Netflix, and 20% subscribe to both. If a student is chosen at random, find the following probabilities. Part A, the student subscribes to Amazon Prime given that he subscribes to Netflix. Right, and so probably the hardest part is translating that question into some sort of probability notation. Okay? And so if we use, if we let A be Amazon, or I guess Prime, should have used a P maybe. Whoa, I don't know what I did there. N can be Netflix. What are we given? In that case, using that notation, then we're given the probability of A is 0.65. The probability of N is 0.5. And what's the 20%? It's the probability of A and N. Right? If you subscribe to both, then you're in the A and N. Now, if you think about a Venn diagram, right, and we have A and N, right, two circles, this overlap would be 0.2. Okay? But the A circle, right, it doesn't care if you subscribe to Amazon Prime, then it doesn't matter, right? We're not taking into account whether you subscribe to Netflix or not, right? You either do or you don't subscribe to Amazon Prime. And so, right, but this A circle incorporates both, right? Only Amazon and or only Prime and or both. And so just for the visual, but you don't need to worry about that. But we do need to translate part A. Maybe I'll just grab it here. We want to find the probability that they subscribe to Amazon Prime given that he subscribes to Netflix. So knowing he subscribes to Netflix, what's the probability that he subscribes to Amazon Prime? Translating this, I think the easiest way to solve this, yeah, I was going to say maybe the only way is to use the formulas in this case. I don't really see a tree happening here. And so A and N, that's good news because we have that divided by the probability of N. 0.2 divided by the probability of N, which is 0.5. 0.2 divided by 0.5 is 0.4, which is nicer to think about, I think, in terms of decimals than fractions. How's that going to be different from the next one? Well, let's find out. We want to find here the probability that they subscribe to Netflix given that he subscribes to Amazon Prime. So this is going to be the probability of N given A. I suspect that these will not be the same, but the probability of N and A, we know, because this is also the probability of N and A. Being able to switcheroo those is key. Divided by the probability of A. I get 0.2 divided by 0.65, I think. 0.2 divided by 0.65. Ugh. 0.30769233077. And that's conditional probabilities. So like I said, you already kind of knew how to solve them. We've already done them, right? Drawing marbles without replacement. Anything without replacement is conditional probabilities, right? It affects the probability of the next card, for example. I think we're going to do it. Let's just do independent events, and then that'll be the end of new material. And won't that be so nice? Wow. I know, right? Just one of those days. Independent events. Okay. So we had conditional probabilities, right? Independent events are exactly as they sound, right? Where the probability of something is independent of other things happening, right? And so, right, in the last section, we considered conditional probabilities, just like it was moments ago. In some examples, the probability of an event changed when additional information was provided, right? So then it's conditional or dependent on information, and that's not always the case. And so the additional information may or may not alter the probability of the event. And so here, let's start with a card is drawn from a deck. So you got a deck of cards, 52 cards, and we're going to find the following probabilities. Part A, we want to find the probability of a king. There are 4 kings out of 52 cards. You draw a card. The probability is going to be 4 out of 52. What about the probability that it's a king, given that it's a face card? We can translate this into our formula, right? Because sometimes it's hard to think about, okay, well, I've got how many face cards? I've got 12 face cards and 4 of those are kings, right? You could get there, right? But let's do some practice, some more practice with the formula. And so that's the probability of a king and a face card over the probability that it's a face card. Now, the probability of being a king and a face card, well, that's the same as being a king because all the kings are face cards, and so that's 4 out of 52. Divided by the probability of a face card, which is 12 over 52. And as we saw, those kind of totals, those 52s, cancel. Or you can use your calculator, right? 4 over 52 is a decimal, divided by 12 over 52 is also a decimal. Right? You don't need to worry about the fractions, but you get 4 over 12. Can't remember what she was playing at there, but I guess we'll find out in the next question. There's usually a reason that she brings stuff in, but I can't remember. Oh, I do remember. So knowing that it was a face card told us something about the probability of it being king, right? Because there's only 12 face cards and all 4 of those are kings, right? And so here, that's what I'll make a note. Knowing it was a face card changed the probability. Right, compared to just the probability of it being a king is 4/52, and you can convert these to decimals, but I can look at 4/52 and say that that's not the same as 4/12, right, because they'd have to be over the same number. So a card is drawn from a deck. We want to find the following probabilities. Well, we already found the probability that it's a king. The probability of a king was 4/52. And I guess maybe let's convert these. It's kind of a nasty one. 0.0769, blah, 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 blah. Let's leave it as a fraction. What about B? We want to find the probability that the card is a king, given that a red card was drawn, I think it should say. Right. So now we know that it's a red card. Right. And then what's the probability of a king? And so the probability of king, given that it was red, well, the probability of a king and red divided by the probability of a red. Or if you just want to reason your way to it, right? There's 26 red cards in a deck of 52, and there's 2 red kings, so 2 out of 26. Or you can use the formula and say, okay, a king and a red is 2/52, and the reds is 26/52. So then I get 2/26. Two over 26, if I make these decimals to compare, then 2/26, I think I said, no, 2/26. I think I said it wrong. 0.076923076. So knowing that it was a red card didn't actually change the probability that it was a king, right? It's just a smaller kind of mini version of the deck, right, in the red cards. So here, notice, knowing the card was red did not change the probability of a king. Yep. It's nice to have confirmation. And that's the idea behind independent events. So here's a definition for us. Wait. 2 events, E and F, are independent if and only if. And so it kind of goes both ways, but if and only if at least one of the following 2 conditions is true. And they go hand in hand, because if one is true, then the other has to be true. But if you're able to show that the probability of E given F is the same as the probability of E, right, then it doesn't care what F was, right? Then you can say that E and F are independent of each other. Okay. And so here, probability of E, I think of it as doesn't care about F. Oops. Right, knowing that F happened, knowing that it was a red card, had no impact on the probability of it being a king. Or vice versa, if I have the probability of F given E is the same as the probability of F, then again, right, F doesn't care about E, and it's just always just going to have the same probability. If the events, here's something to memorize. No. If the events are not independent, then they are dependent. Wow, groundbreaking. If one of these conditions is true, then both are true, right? If one doesn't care about the other, then the other doesn't care about it. Oops. Now, this is the one that everyone loves to abuse, this formula. But two events E and F are independent if and only if the probability of E and F is the same as the probability of E times the probability of F. Yeah. Whereas, if we consider, or I'll say versus the probability of E given F, right? How we usually use this formula, if I had to solve for the probability of E and F, I would need the probability of E given F, which is the probability of E and F, divided by the probability of F. Now, if I want the probability of E and F, I can multiply both sides by the probability of F, bring that over here. And so then I have the probability of E and F is the probability of E given F times the probability of F. That's how you will always be able to find the probability of E and F. Okay? But if and only if they're independent, this is equal to the probability of E, right? If, have I used IFF maybe in logic a while ago? If and only if? IFF. Here's a little fun fact, an LFF. IFF stands for if and only if. There. How many F's can I throw in there? So the probability of E given F is equal to the probability of E if and only if E and F are independent, right, from before. Which means that the probability of E and F, if E and F are independent, then you can use the probability of E times the probability of F. Now, most of the time, I use this to argue that two things are independent or are not independent, right? So if you have each of these three probabilities, right, then you can multiply these two probabilities, and if they're the same as the probability of E and F, then you can say that they're independent. Wow, it's like we're back in logic. Well, kind of. It's gonna haunt us. So we usually use this to prove E and F are, or I'll say, or are not independent. given the probability of E and F, the probability of E and the probability of F, gonna have to read it. We can multiply the probability of E and F, and if it equals the probability of E and F exactly, now if they have to equal exactly, then we can say they're independent. Let's see here. Can I add a page? We can multiply the probability of E by the probability of F, and if it is exactly the same, exactly the same as the probability of E and F, then we can say they're independent. A little bit of proofs in here. Proofs in the pudding. Thanks. I always listen to the videos to make sure I'm not on mute. And knock on wood, I haven't been on mute at all this term, I think. Usually once, so there's still room. But I always listen to it, and it was you hyping me up, saying I could take a moment to have a breath. Yeah. And then I said no. Okay. The table below shows the distribution of colorblind people by gender, which is one of those things where we say typically males are more often colorblind than females. Right? And so now we want to know, well, are these two things independent of each other, right? Or maybe they're dependent on each other, right? Knowing the gender might determine the probability of being colorblind. And so we've got males, we've got females, we've got C, which is colorblind, and N represents not colorblind. Creative. Are the events colorblind and male independent? Yeah. So what we're going to do is we can use the table to find the probability of colorblind and male. We can use the table to find the probability of being colorblind, and we can use the table to find the probability of being male. Nothing to it but to do it here. So usually how I do it is C and M. I put a little question, or I guess a big question mark over the equal sign, just to indicate that, hey, I'm just seeing if these two things are equal to each other. Right? Is it equal to the probability of C times the probability of M? So from the table, the probability of being colorblind and male is 6 out of 100. Still not sure if it's equal to, right? So I do want to see that question mark up above just to indicate that, hey, I'm just seeing if these two things are equal to each other. The probability of being colorblind, right, is 7 out of 100. And the probability of being male in this sample is 52 out of 100. You'll want to use your calculator for this, probably, unless you're a show-off, which is fine. Let's see here, 7 divided by 100, use your brackets, times 52 divided by 100, divided by, come on, I had to restart, 7 over 100 times 52 divided by 100. I get 0.06. Is it equal to 0.0364? Right, 6 over 100 is 0.06. I'd say that's not equal to 0.06. So then the argument is going to be, since the probability of C and M is not equal to the probability of C times the probability of M, we can conclude C and M are not independent. So that's how I generally want you to use this formula. Unless I tell you that these two things are independent, then you're allowed to multiply those probabilities to get that and probability. Any questions about that one? Okay. We're going to do the same thing again. Slightly more complicated, I would say. Just slightly. But turns out we have time, so. And I'm trying to remember. Okay. I actually thought this was the last example, that's why. What? It's not. It could be. It could be. Nah, we're here. We're gonna do it all. In a city with 2 airports, 100 flights were surveyed. 20 of those flights departed late. And then there's some sub-information. 45 flights in the survey departed from airport A. 9 of those flights departed late. And 55 flights in the survey departed from airport B, and 11 of those flights departed late. And we want to know, are the events depart from airport A and depart late independent? So, well, if I want to prove independence, let's start there, right? Then I want to be able to show that the probability of, let's say, airport A and late, is it equal to the probability of departing from airport A times the probability of departing late? And I guess I can write it out. You could just use an L if you want. Right, if you want to show independence, then this is how you're going to do it. And so, okay, which means I need the probability of departing from airport A and departing late. And so I have 9 of the flights from airport A were late. Yeah. But that means that 9 out of the 100 were from airport A and late. And so the probability of airport A and late is 9 out of 100. Is that equal to the probability of A? Well, the probability of A is the fraction of flights out of airport A out of the 100, which is going to be the 45 out of the 100. And the overall probability of departing late was 20, right? Which you could look at 9 plus 11 is going to be 20, or we're given the overall statement, but 20 out of the 100. Don't be a hero. Just use your calculator. 45 over 100 times 20 over 100. Crazy. They are independent. Crazy. Therefore, or I'll say, since the probability of A and, I'll do shorthand L, is equal to the probability of A times the probability of A, L, A and L are independent. Or you could use the words are the events, or depart from airport A and departed late are independent. But I'm more concerned about the using the math to support your statement. So that one's tricky because you have to pull information. There's a lot more numbers there than what we used. And so that's kind of hard, I think. But you can do it. It keeps not wanting to stretch out there. A coin is tossed 3 times. The events E, F, and G are defined as follows. E is that the coin shows a head on the first toss. F is at least 2 heads appear, and G is that heads appear in 2 successive tosses. And we want to find, determine whether the following events are independent. Now, if we have to prove independence, right, then in general, I want to show that the probability of E and F is the probability of E times the probability of F, for example. But I think it's going to be helpful to find each of the individual probabilities, but also the and probabilities that we want here. And to find those probabilities, I think maybe the easiest thing to do might be to just draw a tree. Tossing a coin 3 times, it's not too bad. Your first toss, your second toss, and your third toss. Gets a little wonky. Heads, tails, heads, tails, heads, tails, heads, tails, heads, tails, heads, tails, heads, tails. Heads, heads, heads. Heads, heads, tails, heads, tails, heads. Bless you. Have you guys heard that song Fish Heads? It's like probably well, it's a really old song because I downloaded it on Napster. So That's telling, I guess. But it's like fish heads, roly poly fish heads. Such a stupid song. I don't know why I would have risked jail time to download it, but I did. Yeah, the family computer. Yeah, it was in the kitchen actually. That's later.
Oh, is it?
Yeah. Let's find the probability of E. The coin shows a head on the first toss. Okay. And so I've got 2, 4, 6, 8 possible outcomes. And 4 of those have a heads on the first toss. And then who cares what happens, right? And so the probability of E is 4/8. The probability of F is at least 2 heads appear. And so let's look at, and that's the benefit of drawing out your sample space, is now you can look at it to find it. So it exists. I'm not crazy.
No, I'm just reading the lyrics.
Oh yeah. But did it? I think I got it. Fish heads, roly poly fish heads. And then I don't know.
And then more fish heads.
Oh.
Then it says eat them up. Yeah.
That's ringing a bell for sure. Yeah. At least 2 heads. This one. Nope. Yes. And I have 4/8. Thanks for keeping me focused. What about the heads appear in 2 successive tosses? So now I'm going to remove these, and here I have heads in 2 successive tosses. In fact, I have 3 in 2 successive, or in 3 and 3 successive tosses. Heads, tails. That's good. Heads, tail, heads. No. Heads, tail, tail. No. Tail, head, head. Tail, head, tail. Tail, tail, head. No. So I have 3/8. Now E and F. Let's do the same thing. So now it has to have, the coin shows a head on the first toss, which restricts us to this first kind of cluster of 4 branches. And at least 2 heads appear. 1, 2, 3/4. Probability of F and G, at least 2 heads appear. Well, that's 1, 2, 3, 4. Good. And heads appear in 2 successive tosses, which is here, here, here. 3/4. And the probability of E and G let's remove this. Eek. Nice. E is the coin shows a head on the first toss, so we're restricted to these first 4 branches. And G, heads appear in 2 successive tosses, which is really only the first two. Right, so 2 out of 4. Now we can answer the problem. What? I know, right? Not cool. I'll move it down here. If we want to show that they're independent, then we want to show that the probability of E and F is it equal to the probability of E times the probability of F. We've done all this work, so now we're on easy street. Is 3 over 4 equal to 4 over 8 times 4 over 8? Use your calculator. It's not looking good. 0.25. Oops. It's usually 0.75. Since 0.75 is not equal to 0.25, they are not independent. Let me scoot these down. Same thing again. Probability of F and G, is it equal to the probability of F times the probability of G? Well, luckily we did all that work. Probability of F is 4 over 8. The probability of G was 3 over 8. Oops. 4 over 8 times 3 over 8. 0.1875, which is not equal to 0.75. Not independent. Womp womp. The last one, 2 over 4. 4 over 8. It's 3 over 8. None of these are independent. Boring. Not independent. I confirm I didn't do something weird. E and G. Uh-oh, they have E, the probability of E and G is 1 over 8. I did think that was kind of weird that they were all not independent. Where did I go wrong? No. It's true though. I think they screwed up. I'm feeling good about our 2 over 4, but they have 1 over 8. Still doesn't work. Okay, I'll revisit that. And if there is any edits, I'll edit it before I post the notes. And then I'll issue an erratum on Thursday. That's the case. But I'm feeling good about it. I'll look into it, but I think it's a typo. Sadly, it makes them all not independent. But that last one is supposed to be independent, but not the way we did it. That's okay. And of course, on the final exam, if you tell me that, hey, these are my 3 probabilities, then as long as you do this and know what to do with that, if they're not the same, then they're not independent, right? And that's all I'm going for. In fact, I'll probably give you the probabilities something like this. The probability that Jamie will visit his aunt in Baltimore this year is 0.3. Wow, Jamie, come on. And the probability that he will go river rafting on the Colorado River is 0.5. Come on. Again, if the 2 events are independent, what is the probability that Jamie will do both? So this is one of those scenarios where you're allowed to use the formula because I told you that these 2 events are independent, right? Then that means that we're told that if we let B be Baltimore and C be the Colorado River, I guess it's technically river rafting, but let's just do C. If B and C are independent, we know that the probability of B and C is equal to the probability of B times the probabilities. And if we're told that the probability that he goes to Baltimore is 0.3, and the probability that he goes river rafting on the Colorado River is 0.5, the probability that he's going to do both is 0.3 times 0.5, which is 0.15. I'll say this is the same as both B and C. If we're told that the probability of B given A is 0.4, but we're also told that A and B are independent, then what's the probability of B? Well, if A and B are independent, B doesn't care about A happening, right? And so then, by definition, the probability of B is going to be 0.4. By definition, the probability of B given A is just the probability of B, which is 0.4. Or maybe I'll use a darker color. Therefore, the probability of B is this we could have done in the last section. right? If I have the probability of A is 0.7 and the probability of B given A is 0.5, then we can find the probability of A and B. Right? And so we can use the probability of B given A and write that out. That's the probability of B and A, which is the same as A and B, right? B and A is the same as A and B, divided by the probability of A. Now I have a few of these components. I have the probability of B given A is 0.5. I want the probability of B and A because that's the same as, or maybe I'll do this. They're the same. Divided by the probability of A, which is 0.7. So the probability of B and A, or A and B, is 0.5 times 0.7, which is 0.3. We already saw it when we worked through kind of how do we get to independent events, but this is what we developed for the multiplication rule for events that are not independent. And so then you need the conditional probability. So if the events E and F are not independent, then the probability of E and F is going to be the probability of E given F times the probability of F. Why? Because from the probability of E given F, that's the probability of E and F divided by the probability of F. If I multiply this over here, I get the probability of E and F is the probability of E given F times the probability of F. And same thing goes for F given E. So that's the multiplication rule that you were actually using already way back with tree diagrams, right? When we were using trees to find probabilities, right? When you made adjustments for which marble had already been drawn, right, without replacement, then that is a conditional probability. And so you were multiplying down the branches, multiplying conditional probabilities. We just didn't call it that until this section. Now, I am sad to say that this is our very last example, and then no more new material. Wow. I know, sad. If we're given P of A is 0.5 and the probability of A or B is 0.7, and if A and B are independent, then we're going to find the probability of B, kind of lassoing back to, I want to say 8.2 or maybe even 8.1. What's the formula for the probability of A or B? Is the probability of A plus the probability of B minus the probability of A and B. We're told, let's plug in what we know. The probability of A or B is 0.7. The probability of A, we're told, is 0.5. We want to find the probability of B, so we'll leave that alone. But then we don't have the probability of A and B. But we are told that A and B are independent, which means that I'm allowed to multiply those probabilities. And so that only helps me a little bit, right? The probability of A times the probability of B. Why does that only help me a little bit? Because I know the probability of A, but I still don't know the probability of B. That's okay. I'll put brackets around that. So if I plug in, I'm just going to write out minus 0.5 times the probability of B. I know I need to solve for the probability of B. And so what can I do? I'm going to shuffle everything that doesn't have a probability of B in it to the left-hand side. So I get 0.7 minus 0.5 is the probability of B minus half of probability of B. So I get 0.2 times the probability of B, pulling out a common multiple of probability of B, which is going to be 1 minus 0.5. Or if you just want to talk it out, right, the probability of B minus half of a probability of B gives me half of a probability of B left over. And so, but technically what you're doing is you're pulling out a common denominator and multiplying by 1 minus 0.5. Which leaves us with 0.2 times 0.5 times the probability of B. When it's multiplying, I like to have it out front, but you could leave it behind. So to solve for the probability of B, I get 0.2 over 0.5. It's 0.4. To keep it on one page. And then usually I do like the movies, the end. They lived happily ever after with a probability of 0.4. No. You did it. Yay. Now, just the final exam. Well, a couple of assignments. Final exam. If you have any questions, let me know. Otherwise, we'll talk about the final exam, go through an outline, maybe do some review, might be nice. And that's it. Well, I'll tell you now, because I have just a moment. I've decided to use questions from the test, which I think I've already said, right? But just so you know that there's nothing crazy happening. We just need to talk about what we're going to do on the final from this stuff. See you Thursday.